Last time in phase, I introduced the concept of an ideal solution versus a real solution. For an ideal solution, remember the main assumption is that the interaction between molecules is similar to interactions of molecules of the same species. So interactions between molecules of different species are similar to interactions between molecules of the same species. And for a real solution, that may or may not be the case. So the other textbook I use, the Dahmen Nabisco book, has a really interesting analogy that they use. Imagine you were at a party, and this is a chemical engineering party. So let's say we've got chemical engineers are going to be red. All right, so imagine that you and your two chemical engineering friends are at a party, and imagine the type of things that you would talk about. If they were anything like the chemical engineering parties I went to as an undergrad, you would talk about your classes, your thermodynamics. Definitely you'd talk about fugacity and how confusing it is. But you can imagine that because you share similar experiences, you would talk about things that interest you or that things that you would have in common. All right, so this is not really an ideal mixture. This is more of like a mixture of things with itself. So imagine that I have water and in two different vessels and I'm pouring it into the same container, right? This is a step above an ideal solution where it literally is the same thing. So it's not really a mixture at all. It's just interactions between molecules where you are the molecules. So I'll denote interactions with little dashes. So this is the mixture of the same components. Now imagine next Friday night you go to a party and there are more engineers, but not chemicals. So let's say now you have your same chemical engineering friends and they're still in red. But now let's say you've got some golds in there as well. And golds are going to be mechanical engineers. And say you're mingling at the party and you're mixing and you're still going to be talking to your friends who are chemical engineers, but you might also have some interactions with some mechanical engineers as well. And try to imagine what type of things you would talk to mechanical engineers about. Well, you don't have the same exact experiences, but it's conceivable that you might have some similar discussions. Like you could talk about the differences in thermodynamics between mechanical and chemical. You could ask mechanical why their convention is that heat and work have different signs than what chemical engineers have. Or you could ask them what they learn about in fluid dynamics and how that's different than chemical engineers. But still, the point is that the conversation is centering on stuff that involves engineering. So this would be like an ideal mixture where the components are distinguishable. They're definitely different things, right? Chemical and mechanical are different disciplines. And the analogy here is that you're mixing molecules of different sizes and shape, but they're similar. Right? So they're going to talk about similar things. In other words, the discussions that you might overhear in the ideal mixture are very similar to the discussions that you might hear in the same, let's see, I need a name for the chemical engineering party. This is let's call it a mixture of the same component. All right, now on the other end of the spectrum, now let's say that in addition to engineers, so in addition to our three chemical engineers, but now we are going to have light blue people, which are going to be our art history students or our communications students. Now try to think about what the conversation would center upon at a party between chemical engineers and art history. And maybe you do hang out with art history majors or communications majors. And you can imagine what the discussions might focus on now. The art history majors would be talking about issues relating to art history, which may not be of interest to engineers, and the engineers would be prattling on about thermodynamics and entropy and enthalpy. That would be of no interest to the art history majors. So you'd have to find some different things to talk about. So maybe you talk about the weather or sports or current events or politics or whatever. But the point is that the interactions that you would have with an art history student are going to be very different than the interactions that you would have with fellow engineers, which is not necessarily a bad thing, right? It's good to branch outside of your comfort zone and talk to as many different people as possible. Just drawing an analogy between a real mixture and an ideal mixture, where don't read anything into the connotation of ideal being what you're supposed to have. Right? That's just what they call it. Right? So just again, just an example for illustrative purposes about how the interactions between molecules might be different. All right, so in an ideal, bringing it back to chemical engineering stuff, an ideal thermodynamic property can be written as the weighted average of that pure component's thermodynamic property. So for enthalpy, for instance, H ideal would be equal to, in a binary mixture, X1 H1 plus 1 minus X1. This is X2, by the way. These are the mole fractions of the components, H2. And one more thing to note here, if I perform a little bit more algebra and I work out what the ideal enthalpy is. So let's say I distribute this H2 and then I group things. So I've got an H1 minus an H2 times X1 plus an H2, which is the equation of a line. So this is Y is equal to mx plus b form. So for the ideal case, an ideal mixture will have thermodynamic properties, some thermodynamic properties that are straight lines. Right, so if I had a measurement for what H1 and H2 are, then my y-intercept would be H2 as a function of x. Right, so if I'm plotting H as a function of x, at x is equal to 0, my enthalpy would be some H2. And then depending on whether H1 or H2 were greater, as my X1 went to 1, I would go to H1, where my slope is H1 minus H2. And like I said, not necessarily H1 doesn't have to be greater than H2. It depends on what the identities of the species are. So from there, I introduced the concept of an excess property. And excess properties are the deviation between the actual property and what you would imagine if the solution were ideal. So this is difference between actual versus ideal. Oh, I'm sorry, I'm going to say real here, keep my terminology consistent. Real and ideal solutions. So mathematically, you would say that the excess enthalpy, for instance, would be equal to the real enthalpy, which has no superscript, minus enthalpy of ideal. And when you plug in the definition of ideal enthalpy, you could say it's H minus H1 minus H2, X1 minus H2. And keep in mind that H1 and H2 are relative to some reference state, so the pluses and minuses here could be flipped, right? So it all depends on what the reference state is. You're allowed to set one reference state per species, so that is important. Remember to set one reference per species. Okay, so you can set different temperatures and pressures as your reference for the individual species, but once you set the reference for that species, you cannot change it. So one and only one reference state per species. And in general, in order to specify that, you would need phase, temperature, and pressure. You need to know the number of phases, right, by Gibbs phase rule. So you need to know temperature, pressure, and whether it's one phase or two. If it's two phases, then only one of temperature or pressure. There's one more property that I defined, which is a mixing property. And mixing properties for some thermodynamic properties are the same as excess, but there's a subtle difference here. A mixing property is the difference between the real property, the real solution, and the weighted average of the individual components. And importantly, for properties like enthalpy, the ideal enthalpy was exactly that. This is a weighted average of the components. But so for enthalpy, for instance, excess and mixing properties are exactly the same. But for two properties, entropy and then by extension Gibbs free energy, these two things are not equal. So take, for example, for entropy, in general, the pure component entropies are going to be different than the ideal solution. So for entropy, there is an increase in entropy, simply from the mixing process. In other words, if you are comparing what the ideal solution versus the weighted average of individual components, that property is in general different. So it is different by the following equation, and I won't show you the derivation of this because I think it's a little bit beyond the scope of this class. But the ideal entropy is, so it is the weighted average at first. So x1 times S1 plus x2 times S2. But then there's also some additional parts. So minus R x1 ln of x1 minus R x2 ln of x2. And because x1 and x2 are numbers that go between 0 and 1, this ln term is negative, which means a negative number. R is positive, x1 has to be positive between 0 and 1. So these whole terms are negative, which means if you're subtracting a negative, then you have a net increase in ideal entropy. So minus a minus number is a net positive and increase in entropy, just from mixing. And this reflects the fact that if I take some amount of species A and I put it into a mixer with some amount of species B, then these two things will spontaneously intersperse. Right, so just the process of mixing introduces some change in entropy. Remember, two things will spontaneously mix, two things will not spontaneously separate. So I have to have some appreciation for that. So this stuff is the difference between the mixing property and the excess property for entropy. So just to summarize that, the ideal solution for entropy, entropy is what I wrote above, which means that the mixing property, delta S of mix, is minus R x1 ln of x1 minus R x2 ln of x2. And for Gibbs energy, by using the fundamental property relationship, I can say delta G mix is RT, because it's minus TS, right? It's H minus TS, whoops. RT x1 ln of x1 plus RT x2 ln of x2. So maybe you'll derive these if you go to grad school someday, but for now, don't worry about where these come from. This is rooted in statistical mechanics.